Okay, in this class, today's class, the idea is I want to help you solve the forward kinematics of this robot. Now, please understand, when we talk about the forward kinematics of the robot, then the robot that is shown to you, the robot that is shown to you is something like this. Now, so in this configuration, but this is not the best configuration to identify the coordinate system. Now, what we do is we try to segment the robot into 3 degrees of freedom robot. So this robot has this first joint. Can you everyone see the servo? This is the servo. Don't do this to your robot. This is the broken one, so that's why I'm moving this. So this is the first servo. Can you see the second servo? This is the second joint. Can you see the third servo inside? This is the third joint. So what I want to do is, first and foremost, I want you to visualize this robot. I have given you the configuration diagram, the CAD model like this. But if I want to solve this robot, I'm gonna flip this robot something like this. And I'm going to analyze the first revolute joint, second revolute joint, and the third revolute joint. It is extremely important to understand the geometric relationship between these joints. The first revolute joint and the second revolute joint, they are perpendicular to each other. Can everyone see that? So this is R perpendicular to R. R perpendicular to R. Second revolute joint is parallel to the third revolute joint. So can you see that? So if and understand, when we are solving forward kinematics, we get one solution. When we are solving the inverse kinematics, we can get multiple solutions. So always remember, how do we eat an elephant? In pieces, which means how do we solve a robot? In pieces. So we have 3 equations, Px, Py, and Pz. So we can only solve for 3 variables. So I'm going to consider first degree of freedom, second degree of freedom, and third degree of freedom. Theta 1, theta 2, and theta 3 as one robot, and the remaining degrees of freedom, and this part, the last 3 degrees of freedom, as a separate robot. Now let's focus on the last 3 degrees of freedom. Can you see? We know that first joint is perpendicular to the second joint. Third joint is parallel to the second joint. Everyone understood this? Okay. So the robot that I want to solve for forward kinematics is R perpendicular to R, parallel to R. Everyone understood? Now let's look at the last 3 joints. And these 3 joints are really complicated because something happens which is called as the gimbal lock. And I want to show you what exactly happens. What does it mean by gimbal lock? Now, first, let's identify the 3 joints. This servo corresponds to joint 4. This servo corresponds to joint 5. And there is a servo inside that corresponds to joint 6. 4, 5, and 6. Now, forget about the first 3. Can you see joint 4? The revolute joint here is perpendicular to the second revolute joint, which means joint 4 and joint 5 are perpendicular to each other. Can you see that? Joint 4 and joint 5, they are perpendicular to each other. Joint 6 and joint 5, joint 6 and joint 5 are perpendicular to each other. Can you see? This is rotating like this. This is rotating like this. So which means R4, joint 4, which is R4 perpendicular to R5, perpendicular to R6. Do you agree with me? Yeah. So, no, check this out. This is 4. This is 5. Can you see that this is 4 and this is 5? 4 and 5 are perpendicular. Hold on. Let's not go there. Don't. So it's always eat an elephant in pieces. So go from joint 4 to joint 5, joint 5 to joint 6. And I will answer your question in just a second. But before I answer your question, everyone agrees, and I want you to understand that joint 4, R4, is perpendicular to R5. 4, 5. And R5 is perpendicular to R6. Everyone understood this? Now comes the tricky question. The tricky question here is I want you to think about an end effector position somewhere here. As soon as I have joint 4, and if I have this configuration something like this, I lose 1 degree of freedom. What does it mean? It means whenever two joints they coincide or become parallel, 1 degree of freedom is lost. Now, how actually it's difficult to show you in the articulated robot, but it's very easy to show in a plane. And if you take my robotics 2 class, that's all we are gonna do. We will just look at the flying robots. So a flying plane is nothing but a spherical joint. This is a spherical joint, except that R4, R5, R6 are not physically connected to each other. So I want you to understand the rotation matrices. What you have is you have the pitch, you have the roll, and you have the yaw. So pitch, so Top Gun, Maverick, pitching up, rolling, and yawing. Now understand what happens. Once again, understand this is yaw. This is roll. Yaw, roll. Yaw, roll. Yaw, roll. And now understand, as soon as it becomes 90-degree pitch, roll and yaw, they coincide, which means you lose a degree of freedom. So that's what happens. That is called as the gimbal lock. Whenever you have a gimbal lock, inverse kinematic solution cannot be found. Once again, you are welcome to play with this, and we'll spend a lot of time in robotics too dealing with gimbal lock. Understand, this is pitch, roll, and yaw. So now if the pitch is anywhere less than 90 degrees, you have yaw and roll separate from each other. So you have yaw and you have roll. But as soon as you go 90 degrees, all of a sudden, yaw and roll, they are about the same axis. What does it mean? This comes back to her question. Now let's understand. You have last 3 joint. So when you have 90-degree pitch, this axis and this axis, they are aligned. Understand again, this axis and this axis is aligned. Both of them are parallel, which means the end effector position can be reached either by rotating this joint or by rotating this joint. Does it make sense? Yes. Which means I cannot find out this joint value and this joint value separately. And this happens when it is 90-degree pitch. So the Euler angles that we are looking at, they have singularity at 90-degree pitch. When does 90-degree pitch happens? 90-degree pitch happens when the second rotation frame, you have R perpendicular to R perpendicular to R. The central rotation frame achieves 90 degrees. And in that case, you can't distinguish between 2 axes. So that is what is called as the gimbal lock. Gimbal lock will not give you any problems in forward kinematics. but gimbal lock will give you headaches in inverse kinematics. And that is not the physical limitation of the robot. That is the limitation of the Euler angles. So to avoid gimbal lock, what we do is we use something called as quaternions or Euler parameters, or we use the complete direction cosine matrix. That is one technique that is used in computer graphics, games, to avoid gimbal lock. And we solve the forward kinematics and inverse kinematics using quaternions. That is coming next. So whatever analysis that we are doing here, you will realize the Euler angles, rotation matrices will not handle gimbal lock, but quaternions will. Everyone understood this? So in today's class, what I'm gonna do is I'm gonna solve this robot. Once again, here is the takeaway. This is the kinematic position that I'm gonna analyze this robot. Now, when you solve this kinematic position, please understand the zero angles that you have assumed could be different than the zero angles in the robot. What does it mean? It means whatever forward kinematics we are working out, it will not give you the exact same results on the software. Why? Because note that on this robot, there are calibration points. Have you seen the calibration point? Yes. So for this robot, it shows that this is its 0, 0. Then this is its 0, 0. But our 0, 0, looking at the way we have configured, is the 0 degrees for the robot plus 90 degrees. Which means if you want your forward kinematic solution to match the forward kinematic solution that is coming from the robot, you need to add plus or minus 90 degrees in your code to account for the changes in the configuration diagram. Everyone understood this?
Why is it that you only have to add 90 degrees in some joints, but not others?
Okay, the reason for that is, please understand, and we have done this in the very first lab. Can you see these calibration points? Calibration points aligned, which means the robot is home. So this is the 0 angle for the first joint. This is the 0 angle for the second joint. Now the way I'm gonna draw this and I'm gonna solve this, it's easier to solve, is I'm gonna assume this to be something like this. Which means in my rest position, the calibration points have a 90-degree offset. So if I want my solution to match the solution that is coming from the MyCobot software, I need to take into account this 90-degree offset.
So if we are able to like calculate the whole forward kinematic in the configuration position, like 0, 0.
If you are able to find out the configuration, if you use the configuration diagram, something like this, that is totally fine. You don't have to add 90 degrees. But I have found, based on my teaching, I have found out it's difficult to solve the robot in this configuration, at least initially. Students understand this better if I actually draw the robot something like this. So I'm gonna solve the robot like this. You are more than welcome to modify that formulation for this. Then your forward kinematics will be same as the forward kinematics from MyCobot. But for sake of simplicity, I'm gonna draw R perpendicular to R, parallel to R, like this. Any questions?
Also regarding that gimbal lock that you told, does that mean that joint 5 and 6 are kind of useless in terms of rotating the end effector, or like?
No, what it means, when the joint 4 is at 90 degrees, joint rotation of joints 5 and joint 6 equal aligns, which means they don't have independent solution. In terms of linear algebra, if you have the joint rotation of joint 4 and rotation of joint 6 about the same axis, the final result you cannot distinguish. Example, if the final orientation is 30 degrees, you do not know that. Silence, please, is extremely important. Once again, what is happening in gimbal lock? In gimbal lock, joint number 5 is at 90 degrees. Joint number 5 is at 90 degrees, which means joint 4 and joint 6 are parallel to each other. Now, if I give you a joint value, say 90 degrees, you do not know for sure that 90 degrees is the final orientation. Is it 10 degrees of joint 4 and 80 degrees of joint 6, or 40 degrees of joint 4 and 50 degrees of joint 6? So you can't uniquely find out those two values, and that is gimbal law. Does that answer your question?
Geometry.
So basically what it means is the matrix becomes singular. If you take linear algebra, in the linear algebra, you need 3 independent bases, which means what it means is you need to have 3 perpendicular axes. If in one configuration, if your axes are going to collapse, that means you don't have unique solution for those 2 axes, right? That's what is happening. Everyone understood about singularity? And I would encourage you, when you play with the my cobot, set joint 4 to 90 degree and see that IK solver will start showing you errors. Once again, you can analyze the whole thing like this. So you have R perpendicular to R, parallel to R. This is the first 3 joints. Second joint. And the second part of the robot is you have R perpendicular to R, perpendicular to R. Everyone understood this? And when the joint which is in between achieves 90 degrees, now what I want to show you is, again, check this out. Now and I want you to do this. So this is, I'm spending way too much time. So joint 4, joint 5, and joint 6. Do you agree with me? Joint 4, I don't know if you can see this. The calibration marks are aligned. Joint 5, can you see the calibration marks are aligned? And joint 6, the calibration marks are aligned. Do you agree with me? In this configuration, you can independently find out joint value of 6, joint value of 5, and joint value of 4. Everyone understood this? However, when joint 5 becomes 90 degrees, so I'm gonna make this joint 5 90 degrees. Once I make this plus 90, or once I make it, it doesn't do minus 90. If I do it plus 90, can you see that joint 4 and joint 6, both the axes are aligned? So which means if your final orientation is 90 degrees, you do not know how much of 90 degrees is given by joint 6 and how much of 90 degrees is given by joint 4. Which means you cannot uniquely find these 2 solutions. And why is that? Because this axis and this axis is parallel. To solve these, we need to have a triad, right? If your axis collapse, you cannot find out the 2 angles separately. Everyone understood? Exactly the same thing happens in the aircraft when it is pitching 90 degrees. Yes.
So, what will happen if it's backwards 90 degree, minus 90?
No, minus 90 degrees, same problem. The only thing is this robot cannot go minus 90 degrees.
Okay.
But if it were to go minus 90 degree, exact same problem. This axis and that axis get aligned. And that is the meaning of gimbal lock. Gimbal lock means this axis and this axis, they are aligned. So you can achieve the same orientation. You can achieve the final orientation by infinite combinations of these 2 orientations. Everyone understood this? So now we are gonna work out the forward. So how do we do forward kinematics when you have R perpendicular to R? The easiest way to solve this problem is don't treat the central rotation as 90 degrees. What does it mean? It means align the marks like this. Now I want you very carefully to understand the axis. Joint 4 going like this. Do you agree with me? Joint 5 going like this. No, joint 5 going like this. Joint 5 going like this, and joint 6 going like this. Can you see that joint 4 axis is perpendicular to joint 5 axis, which is perpendicular to joint 6 axis? Everyone understood this? As soon as I do it 90 degrees, check this out. What happens? Joint 4 axis, joint 5 axis, joint 6 axis. Gimbal now. Everyone understood this? All right. By the way, don't move robot by hand. This is a broken robot. That's why I'm actually getting this to show you. You are welcome to take a look at it. Anyway, I'm gonna fix it because I need to change some of these servos. But this is the robot that you have. I'm gonna use the basic position, and I will work out the problem. Okay, so what I have is I have a robot R, silence please, perpendicular to R, parallel to R. This is my first 3 degree of freedom robot. Then I have R perpendicular to R, perpendicular to R. This is my second robot. So what I'm gonna do is, first I'm gonna solve the transformation 0 H3. I will find out 0 H3, and then I will find out 3 H6, and then I will multiply 0 H3, 3 H6 is equal to 0 H6. Everyone understood this? Now I'm gonna draw the first robot. This is the first revolute joint. This first revolute joint is perpendicular to the second revolute joint. This is R. This is R. And then what I have is I have this second revolute joint. Parallel to the next revolute joint. And then I'm gonna have an end effector here. So I have this R perpendicular to R, parallel to R. And I will work out the spherical wrist separately. I'm gonna give you some dimensions. This dimension is going to be, and I need to be consistent in terms of the code that we have. This dimension is going to be A1. This dimension is going to be A2. And this dimension is going to be A3. So you have A1, you have A2, and you have A3. Now we need to set up the coordinate frames. Always remember the z-axis must pass through the joint. So I'm gonna call this as my Z0. I'm gonna call this as my Z1. I'm gonna call this as my Z2. So once I get my z-axis, I need to complete the triad. This becomes x naught. X naught can be anywhere, okay? I'm just assuming x naught in this direction. Right hand coordinate system. So I have z, x. So this becomes y. So this is y naught. Now second coordinate frame, what I need to do is, I need to find out x1. So x1, remember the rule, x1 should intersect with z1 and z0. x1 should intersect z0 and z1. And you can see that is only possible if I use my x1 something like this. Now some of you may ask me, why can't I use my x1 like this? Now please note, this is not intersection. It's basically x1 is parallel to z1. But if I draw x1 like this, x1 is intersecting with z1 and x1 is intersecting with z0. Everyone understood this? Finish the next part. So you have x1, you have z1, and then you have this as y1. Now same thing here, we have z2. Now I need to find out x2. To find x2, this is gonna be x2, because then x2 would intersect z2 and x2 would intersect z1. X, z, and you get y, something like this. Is y2. And the last coordinate frame, I'm just going to replicate y3, x3, z3. Everyone understood this? So this is my first robot. I have R perpendicular to R, parallel to R. And now I'm going to use the technique that we talked about. So first 0R1. The only transformation that you should be remembering is cosine. So let's identify the angles. So curl your fingers in the direction of Z1. This becomes my theta 1. Curl your fingers in the direction of Z1. This becomes my theta 2. Curl your fingers in the direction of Z2. This becomes my theta 3. So once again, the Z0 axis is going through joint 1. Z1 axis is going through joint 2. Z3 axis is going to joint 3. So again, you have Z0, Z1 and Z2. Theta 1 is about Z0. Theta 2 is about Z1. Please note, curl your fingers in the direction of rotation and the rotation is positive. So these are all positive values. So you have cosine theta 1 minus sine theta 1, 0, sine theta 1, cosine theta 1, 0, 0, 0, 1. And don't forget the projection matrix. The projection matrix is projection of new frame onto old frame. The new frame is x1, y1, z1. Old frame is x0, y0, z0. I want you to look at x1. Can you see x1 and x0? They are in the same direction. So I have one here, 0, 0. Can you see y1 and y0? They are in the same direction. Can you see y1 and y0 are in same direction? So 0, 1, 0. No, no, sorry. Y1 is in the Z. Okay, you're right. Y1 is in the same direction as Z0. Z1 is in the direction of minus y0. Are you with me so far? Check this out. Silence, please. Y1 is going up. Can you see Y1 is going up? And that is aligned with Z0. So Y1 is aligned with Z0. But Z1, as you can see, Z1 is aligned with minus Y0. Why? Y0 is going in that direction. Z1 is coming in this direction. They are opposite to each other. Everyone understood this? So now, once you perform this multiplication, you have your rotation matrix. First row, first column, cosine theta 1. First row, second column, 0. First row, third column, sine theta 1. Second row, first column. Everyone knows how to multiply matrices, right? Anyone here does not know how to multiply matrices? Sine theta 1. Then this becomes 0. This becomes minus cosine theta 1. This becomes 0. This becomes 1. This becomes 0. Are you with me so far? Now we need to come up with the homogeneous transformation. The homogeneous transformation is 0, H1. And what we will do is, we will actually get this rotation matrix, plug this in here. Sine theta 1, 0, minus cosine theta 1, 0, 1, 0, 0, 0, 0, and I have 1 here. Now, the last part, the last column of the homogeneous transformation is I need to find out the distance between the frame 1 and frame 0 with respect to the 0th coordinate frame. Once again, the distance between the first frame and the 0th frame with respect to the 0th coordinate frame. Can you see that the frame 1 and frame 0, there is no x offset? Do you agree with me? There is no x offset. So this becomes 0. Frame 1 and frame 0, there is no y offset. Can you see that? The only offset they have is with respect to Z0, which is nothing but A1. And this is extremely important, so I'll spend some time over here. Homogeneous transformation, silence please. Homogeneous transformation encodes the information about the rotation and the translation. The trick here is the translation between the previous frame and the next frame should be expressed in the coordinate frame of the previous frame. What do I mean? If you look at the second frame, you have y1, x1, z1, but that is not the coordinate frame that I'm gonna choose. I'm gonna stick to x0, y0, and z0 and find the different distances between the 0th frame and the first frame. Everyone understood this? So when you find the distances, ignore the coordinate frame of frame number 1, which is x1, y1, z1. Just look at x0, y0, z0. How far the frame 1 is with respect to x0, y0, z0 in the coordinate frame x0, y0, z0. Everyone understood this? Yeah. That's why I have 0, 0 and just a1. Because that distance, no matter what you do, is going to remain fixed. So this distance is always going to remain fixed. Everyone understood this? So this is my first homogeneous transformation. Now I'm gonna go for the second homogeneous transformation. Same story repeat, 1 or 2. Are you with me? The only matrix that you should remember is cosine theta 2 minus sine theta 2, 0, sine theta 2, cosine theta 2, 0, 0, 0, 1, and multiply that by the projection matrix, and this will always be projection of the new frame. What is the new frame here? X2, Y2, Z2. What is the old frame here? X1, Y1, Z1. Now, I want you to look at X2. X2 is aligned with X1. Do you agree with me? Same direction, arrow pointing in the same direction. 1, 0, 0. Y2 is aligned with Y1. Do you agree with me? 0, 1, 0. Z2 is aligned with Z1. Can you see? Same direction. 0, 0, 1. This is an identity matrix, so I don't have to multiply. Do you agree with me? So I'm gonna write the homogeneous transformation 1H2 as cosine theta 2 minus sine theta 2, 0, sine theta 2, cosine theta 2, 0, 0, 0, 1, 0, 0, 0, and I have 1 over here. Now, next thing, what we want to do is, we want to find out. So here is the critical part. Frame number X2, Y2, Z2. How far is it from frame X1, Y1, Z1? Assuming the coordinate reference frame X1, Y1, Z1 for all values of theta 2. Can you see that this becomes A2 cosine theta 2 and A2 sine theta 2, and this becomes 0. Are you with me? Once again, I want to show you this in terms of the robot. This is my R1. This is my first frame X0, Y0, Z0, X1, Y1, Z1. And now what I'm looking at this angle. And I want to make sure that for all the values of theta 2, I find out the distance between the frame number 3 and frame number 2 and frame number 1. So this is like the cosine component, and then I have the sine component. Sine component is this, cosine component is this. So I have this is, and the last part is 2R3, and same thing, 2R3 is going to become cosine theta 3 minus sine theta 3, sine theta 3, cosine theta 3, 0, 0, 0, 0, 1. Multiplied, yeah. Yeah, so the coordinate frame of the end effector, if you align that coordinate frame with the previous coordinate frame, your projection matrix would be identity. That is the reason why, understand, the end effector does not have any joint. So there is no restriction that Z3 needs to be aligned with Z2. Z3 can be anywhere because there is no joint. But as soon as I have Z3 aligned with Z2, X2 aligned, X3 aligned with X2, and Y3 aligned with Y2, my projection matrix becomes identity. Everyone understood this? So I saw, I actually gained some efficiency there. But I'm gonna do this once more again here. I have X3, Y3, Z3, X2, Y2, Z2, 1, 0, 0. Because X3 is aligned with X2.
On model 1 and 2, there's also an offset in the 3 direction, like 66.
Yeah. So what you will have in terms of you're talking about the cobalt, right? Yeah, then you have to add that, you have to change the formulation.
Yes, also sir, like we are taking C in the same direction for both the motors. But in the forward, they are in opposite. Like if you are going to give any rotation and if you are taking C in the same direction, then the curl is going to be different. Like motor 1 and 2, they are in opposite directions. Like in terms of rotation,
Yeah, so again, what I'm doing is I'm solving this for the simplistic case. If you want to extend this formulation to cobalt, it's not one-to-one correspondence. You have to take into account the offset, you have to take into account the direction of rotation, because the servos could be mounted the opposite direction. The positive value for servo may be negative value for this. So this is not one-to-one translation, so you will have to modify this a little bit. But that's why the lab 2 is for, right? So 0, 0, 0, 1, 0, 0, 0, 1. And I'm gonna write down 2H3, and that 2H3 is cosine theta 3 minus sine theta 3, sine theta 3, cosine theta 3, 0, 0, 0, 0, 1, 0, 0, 0, 1. And again, the same logic. This is going to be A3 cos theta 3, A3 sin theta 3, and then you will have 0. And now you have these homogeneous transformations. Everyone understood this? The next part is we are gonna go to MATLAB and program these homogeneous transformations in MATLAB and ask MATLAB to perform the calculation. Yeah.
you mentioned that we take the second motor, we turn it to 90 degrees, right? And you mentioned that like if you want to convert it to the cobalt, you need to.
You don't have to. You don't have to. You can actually work out the forward kinematics just like this. If it's easier for you to visualize, I just find that showing robot like this makes it easier for you to understand. In this configuration, in the past I found out the students found it difficult because the axes were not matching. That's why I thought use this configuration, but you are welcome to find out the forward kinematics. Yeah, but otherwise, silent please. Or you can work out the forward kinematics in the 0, 0 coordinate frame of the robot. So where the calculation points are aligned. That's totally fine. And then other thing is just like what he said, I have assumed that the zero frame, which is x0, y0, z0, is aligned with x1, y1, z1. That may not be the case. There could be slight offset. So basically, that you will take into account in the homogeneous transformation. Everyone understood this? But that's a fixed offset. That is not going to change. So you have to modify the homogeneous transformation accordingly. Any questions before I go to skeletal risk? Yes.
Can you explain how we know if we should take the sign of the first and the homogenious function? Like the.
So the sign, so this is the only matrix that you have to remember. Cosine, cosine, sine, sine, cosine. Because that is the rotation matrix about z. Our joint is always about z axis. So I don't want you to remember any other transformations. Only the rotations about z. And that is the reason why the first joint is rotating about z naught. The second joint is rotating about z1. And the third joint is rotating about z2. So the only rotation transformation that you should remember is cosine minus sine, sine, cosine. Everyone understood this?
Why is you and why? How will be aligned?
What?
Why is you and why?
So
Like, why is they're not aligned. So we have to this with that.
So what is your question? Y1 and Z0 are aligned. That's why in the projection matrix, you have Y1, the entry here is, so can you see that this entry is Y1 is aligned with, yeah. X2 would never intersect Z1. X2, okay. It's a coordinate system. Coordinate systems, it has an axis. It can extend in the forward direction and in the backward direction. So which means if I were to say X2, X2 basically gets extended all the way over here. And can you see it is intersecting with Z1? Silence, please.
The new x1, x1, y1, z1 is representation to x0, y0, z0. We can directly come up with cos theta 1, 0, sin theta 1, right? Because the projection of the new frame onto the older frame can be understood by the theta 1 rotation.
You can do that, but I recommend that rather than jumping steps, follow these steps and you won't get the answer wrong.
But this is the thing I did in my. What I did is I took the projection to the older from x1 to x0, and then I multiplied it again with the projection matrix. So I'm a bit confused. Like, what is the need of creating the new matrix in x7 with respect to x2?
I will answer your question after the class. And I would discuss that in detail, but I would like to finish spherical wrist so that the students can finish the lab. So please bear with me. Everyone else, please follow this procedure. You are welcome to jump steps once you become comfortable. I have had students who actually did not even write the whole thing. If you use the Quaternion approach, you don't have to worry about it. You can just write the forward kinematics in one shot. In one line, you can solve the forward kinematics. But till we get to the part, please follow these steps. Everyone understood this? So always remember, you have the rotation matrix. That rotation matrix is not going to change. Cosine minus sine, sine, cosine. That would be your standard rotation matrix. And the projection matrix would flip it depending upon whether the rotation is about x, about y, about z. Everyone understood this? So follow this rule and then you will not get forward kinematics wrong. Next part is, before I solve the spherical wrist, what I want to do is I want to restate the rules for my satisfaction. First rule is z-axis through joint. Second rule, xn axis intersects Zn, please understand it is redundant because xn is perpendicular to Zn, so it has to intersect. Okay, if it's not intersecting, which means it's not a triad. So xn is intersecting Zn and Zn minus 1. So that is the key thing. And please understand, intersection means physical intersection. It's not being parallel. It needs to be perpendicular and intersect. And the last rule that I want you to remember is you are going to use right hand coordinate system. Now, sometimes it is not possible to follow the rules exactly. In certain cases, you cannot follow the rules exactly, and at that time, you have to consider the exceptions to the rule. Example. Imagine now what you have is you are trying to solve the last three joints of this robot. You are trying to solve last three joints of the robot. Once again, joint 4, joint 5, and joint 6. They are perpendicular to each other. Whenever you have the three revolute joints that are perpendicular to each other, you have to set up the problem in a sequence so that the joint axis of the fourth joint or the first joint is perpendicular to the joint axis of the second joint, and the third joint is perpendicular to the second joint. So do not set up the problem like this. Everyone understood this? Do not set up the problem like this because the forward kinematics formulation will be very complicated. Set up the problem wherein the first joint and the second joint, they are perpendicular. Second joint and the third joint, they are perpendicular. Everyone understood this? Again, this is the case R perpendicular to R, perpendicular to R. Now, what I'm going to show here is I'm going to show a very generic case of R perpendicular to R and perpendicular to R. Now, this is the second joint. Once again, I want you to imagine if this joint becomes 90 degrees, can you see the rotation of this joint gets aligned with the rotation of that joint and we lose a degree of freedom? Yes. That is the gimbal lock. Do not attempt the problem in gimbal lock. Please understand, you need to have three perpendicular axes to set this problem up. So I'm going to set up the coordinate frame. This is going to be my Z0. This is going to be my Z1. This is going to be my Z2. And I will just show here, this is going to be my Z3. Now, X0 is going to be like this. X0. My Y0 is going to be like this. Now, Z1 is like this. Now, what I want you to do is, I want you to tell me where should I draw X1? How should I draw X1? Can I draw X1 like this? So if I draw X1 like this, now please understand, x1 is intersecting with z1, x1 is also intersecting with z0. So which means my rule number 2 is satisfied. And then this is my x, this is my z, so this becomes my y. y1. Once again, this is my x1, and I'll be very clear here. So can you see my x1 is intersecting with z1? My x1 is intersecting with z0. Everyone understood this? Now comes a very, very important question. Everyone, look at the board and tell me, where should I draw x2? Okay, if I draw x2 here, if I draw x2 here, x2 is intersecting with z2. But is x2 intersecting with z1? No. Everyone see that? My x2 is here. My z1 is here. So they are not going to intersect anyways. They are always going to be parallel. Okay. Let's try another option. How about this? So now everyone understands that we are helpless. No matter what we do, our x2 is not going to intersect z1. Which means the rule number 2 that I have shown here will not be satisfied no matter how I draw it. Everyone understood this? Yes. So this is where you have exception to the rule. This is a very important case. So now, again, since we don't have any other choice, what I'm gonna do is, I'm gonna assume my x2 to be something like this. You can assume x2 in other direction also, but x2 like this. So check, I have x2, z2. So this is going to be my y2. Are you with me so far? Once again, the rule is not satisfied. Rule number 2 is not satisfied. Rule number 1 is satisfied. Rule number 3 is satisfied. Rule number 2 is not satisfied. Everyone understood this? It's really important. Understood? Yes. Okay. Now what I'm gonna do is, I'm gonna go a step further. And here, for the last coordinate frame, I would just replicate the previous coordinate frame, x3 and y3. Now I'm gonna call this distance a1. I'm gonna call this distance a2. And I'm gonna call this distance a3. Now here, please note, rule 2 not satisfied as x2 is not intersecting c1. Everyone understood this?
Yes.
Now what do we do? Whenever you have a case like this, what we do is, we do a frame translation. What do I mean by frame translation? So technically, our coordinate frame z2 needs to be located at joint 2. But since the rule is not satisfied, I'm gonna translate this frame from its current position to the previous frame position. So what does it mean? So please pay attention. We start the setup something like 0 R1. 0 R1 is the rotation theta 1, theta 2, and theta 3. So this is theta 1, theta 2, and theta 3. 0 R1 is going to be cosine theta 1 minus sine theta 1, sine theta 1, cosine theta 1, 0, 0, 0, 0, 1. Multiplied by the projection matrix, which is x1, y1, z1, x0, y0, z0. Now please note x1 is aligned with x0, y1 is aligned with z0, and z1 is aligned with minus y0. Are you with me? So what I have is I have the final transformation. First row, first column, cosine theta 1. First row, second column, 0. First row, third column, sine theta 1. Second row, first column, sine theta 1. Second row, second column. Second row, third column, minus cosine theta 1. Actually, and then the last is 0, 1, 0. Let's not forget the homogeneous transformation. 0 H1. Silence, please. 0 H1 cosine theta 1, 0 sine theta 1, sine theta 1, 0 minus cosine theta 1, 0, 1, 0, 0, 0, 0, and I have 1 here. The key observation here is this setup is exactly same as the previous setup. So my x1, so my x is going to be 0, my y is going to be 0, my z is going to be a1. Are you with me? This is my first homogeneous transformation. Now, what happens is I want to do the second homogeneous transformation. For second homogeneous transformation, understand frame number 2 is not following the rules. So what I'm gonna do is I'm gonna translate frame number 2 onto frame number 1. What does it mean? It means, I want everyone to pay attention to this. I'm gonna physically take that frame and move it to here. So I'm gonna move that frame over here. So now this is my x2, this is my z2, and this is my y2. So this frame got moved over here, and as soon as I move this frame, as soon as I moved that frame x2, z2, and y2 from its original location onto the previous frame, can you see all the 3 rules are satisfied? Are you with me? All the 3 rules are satisfied. So technically, what did I do? I actually translated the frame from its current location to the previous location, which means in this new configuration, my x2, y2, z2 and my x1, y1, z1 are at one and the same point, which means there is no translation. Because now these 2 frames are on top of each other. Everyone understood this? Okay, so what I'm gonna do is, I'm gonna do the exact same thing and I will write it over here. So I would say 1 R2, again cosine, let me use a different color pen. So 1 R2 cosine theta 2 minus sine theta 2, sine theta 2, cosine theta 2, 0, 0, 0, 0, 1. And then I have x2, y2, z2, and I have the previous frame x1, y1, z1. Now, can you see? Now I need to look at the green frame. x2, so I will use this. x2 is aligned with y1. x2 is aligned with y1. y2 is aligned with z1. And z2 is aligned with x1. So which means my 1R2 matrix is going to be cosine. So it becomes minus sine theta 2, 0, cosine theta 2, cosine theta 2, 0, and then it becomes sine theta 2, 0, 1, 0. Are you with me? Now please note that I translated the frame translation. Why did we do the frame translation? Because rule number 2 was not satisfied. As soon as I translated the frame, everything is satisfied. Everyone understood this? Now comes the part I need to construct the homogeneous transformation. I need to construct the homogeneous transformation. But in this case, homogeneous transformation is extremely simple. Why? Because these two frames do not have any relative transformation. No translation in X, no translation in Y, no translation in Z. Both these frames are on top of each other. Everyone understood this? So I can write the homogeneous transformation just 1H2 as minus sine theta 2, 0, cosine theta 2, cosine theta 2, 0, sine theta 2, 0, 1, 0, 0, 0, 0, 0, 0, 0, 1. And why do I have these zeros here? Because the frame coincide. Everyone understood this? Now comes the next part. Now the next part is, what are we gonna do with the frame x3, y3, and z3? Now, what this means, right now, when we are trying to solve this problem, I want you to look at the problem like this. So you have this first joint. You have this first joint. Then you have this second joint. You have this second joint. And then this second joint has this third joint. You have this third joint. Now, this third joint, so theta 2. So check this out. This is x3. Z3, x3, and y3. And for the sake of solving this problem, what we have is we have x2, we have y2, and we have z2. So this frame was over here, but this frame got translated from this point all the way to this point. And I'm interested now, it's extremely important. Please note that there are two dimensions here. One dimension is A2. And the second dimension is A3. Now the last coordinate frame that the transformation that I'm gonna write down is extremely important and a little bit tricky. So I want you to pay attention. Since we had the rule violation, I translated the frame that was at this location all the way over here. Now for analysis purposes, I'm gonna treat this frame and this frame. First and foremost, let's write down the rotation matrix. Let's write down the rotation matrix. Rotation matrix is 2R3. Because check this out. We got 0R1, we got 1R2, so we need to find out 2R3. Do you agree with me? Rotation matrix is not going to change. Rotation matrix is cosine theta 3 minus sine theta 3, sine theta 3, cosine theta 3. 0, 0, 0, 0, 1. Do you agree with me? Let's not forget the projection matrix. Projection matrix is gonna be x3, y3, z3, x2, y2, z2. And check this out. x3 is aligned with x2. Can you see that? x3 is aligned with x2. z3 is aligned with z2. And y3 is aligned with y2. Y3, no, z3 is aligned with z2. And y3 is aligned with y2. Which means now what I'm gonna write my homogeneous transformation. My rotation matrix is going to be, since this is identity, silence please. Last part is extremely important. Cosine theta 3, sine theta 3, 0, sine theta 3, cosine theta 3, 0, 0, 0, 1, 0, 0, 0. I have 1 here. And now I want you to tell me, what should I write here? What should I write here? And what should I write here? Once again, I'm looking at the distance between frame 3 and frame 2 measured with respect to the coordinate frame x2, y2 and z2. Can I understand? Hold. Let me develop this argument. Can you see that if I look at my x3 and my x2, my z3 and my z2 and my y3 and y2, the only distance that I have in between the coordinate frame 3 and coordinate frame 2 is about z2. And that distance is a2 plus a3. So I would have, extremely important, 0 here, 0 here, and a2 plus a3 here. No cosines, no sines. No cosines, no sines. So this will be something like 0, 0, a2 plus a3. And your homogeneous transformation is going to be 0h3 is equal to 0h1 multiplied by 1h2 multiplied by 2h3. Are you with me? Correct. Correct. Let me explain this once again. Now, before I explain this, I want you to understand what is happening here. Have you noticed that whenever we have a transformation, this sine cosine theta to sine theta to, we take the projection because the angle rotates. The angle rotates. Here, if you look at the way the problem is set up, the distance between the frame 3, which is x3, y3, z3, and x2, y2, z2 is only offsetted by z2. There is no offset in x. There is no offset in y. The only offset is in z. And please note, no matter whatever the angle of z3 is, no matter whatever the angle of theta 3 is, the distance between these two will always be in z2. Once again, imagine you have rotation theta 3. You have rotation theta 3. Theta 3 rotation is about this, right? If you have any rotation about theta 3, your z2 is not going to change. And your distance will always be with respect to z2. Everyone understood this? That's why you will have A2 plus A3. And once you combine the previous forward kinematics with the forward kinematics of this. So what we have done today is we have looked at the forward kinematics of R perpendicular R parallel to R and R perpendicular R perpendicular R. When you combine these two, you would get the forward kinematics of cobalt. And we'll stop here.